Okay, hello and welcome everyone to today's EurJOC virtual symposium, Meet the Chemist. I'm Charlotte Panther, the deputy editor of EurJOC, and it's my pleasure to be your host for today. This is the fifth event of our series that we started earlier this year in February. And at the time, we didn't quite anticipate that these events would become so popular. And if I'm being really honest here, we weren't even sure that it would be more than a one-time thing. But now, 5 events later, 13 speakers, and almost 3,000 attendees, we're very glad that Burkhard König, the chair of our editorial board, convinced us to give this experiment a try. It's been great to see that each of our symposia has attracted new participants from all over the world, but it's also been great to see that some of the participants from the very first event are now with us here today. I would like to take this opportunity to thank everyone involved in the previous events and in today's event for making this series so successful. As this will be our last event for the year, we decided to close 2020 with a bang. We invited Tati, Fernández-Ibáñez and Joseph Moran to present today. After their lectures, we will have a Meet the Chemist session in which Tati, Joseph, and Burkhard will discuss tips and tricks ranging from how to apply for PhD and postdoc positions and how to choose a research topic. You're very welcome to post any questions to Tati and Joseph in the chat. Please make sure to mention to whom this question should be addressed by adding Tati or @Joseph to your message. Before we start with the scientific program, I would like to pass the mic to your EurJOC editor-in-chief Ángeles for a very special announcement.
Thank you very much, Charlotte, and also a warm welcome from my side to the last EurJOC virtual symposium. It's now my pleasure to introduce or to present the first EurJOC Lecture Award. And the idea for this award arose at a board meeting that we held virtually earlier this year. And the aim was to highlight the best paper submitted by a young researcher. So first, the editorial office made a pre-selection of papers submitted in 2019 by early career researchers. We then had our editorial board look at these papers, and I'm happy to share that close to 70% of our board members participated in the vote. And I'm now happy and proud to present the first winner of the EurJOC Lecture Award, and I'd like to share the following slide with you and announce the winner. Thank you, Charlotte. Okay, good. So the slide is now up, and the winner of the 2020 Lecture Award is Professor Gui Jinghan from the Shanghai Institute of Organic Chemistry for his paper titled Modular Synthesis of Functionalized Butylolides by Oxidative Furan Fragmentation. I'm also very happy that Jihan is with us today here live at the symposium and will accept the award. Professor Gui studied chemistry at the Anhui Normal University in China, and he moved then to the Shanghai Institute of Organic Chemistry for his PhD studies. And he received his PhD in 2012 under the supervision of Professor Tian Weisheng. He then stayed on at the SIUC for another year as a research associate before moving to the United States. And here he took on a position as a postdoctoral associate with Phil Barron. He then returned to the SIUC in 2016 and has been a professor at the Institute since. His research interests lie in the synthesis of complex natural products, and here in the development of simplified and also new methodologies. Professor Gui's paper was already was invited as part of our EurJOC Young Talent series and already received a lot of attention when it was first published and highlighted in this series. And now I'm very happy to award Jihan for this paper with the award. So congratulations from the whole editorial office for winning the award for this outstanding paper. And I would also now like to hand over to, congratulations, Jihan. And as our board was heavily involved in, first of all, selecting the paper and in creating the award, I would also now like to hand over the word to Burkhard to say a few things and also congratulate you.
Yes. Jan, I also would like to congratulate you to this great work. It was very nice to see the selection process through the editorial board, and it was nice to see all the great comments. I think your work is a tremendous contribution to the organic synthesis on there, because these butynolides are, of course, very important compound classes, and I think your access by these straightforward oxidation of furanes is a great addition on there, and I think this was well received by many of the board members. So congratulations again, and I very much look forward to hear more about this chemistry, and I think I have the chance to do so in the near future. And with this, I give back to Anne, maybe to just lift the secret, no?
Yes, thank you very much, Burkhard. Yeah, of course, a lecture award would not be anything without a lecture. And so we have actually invited Jihan to speak at our next virtual symposium, which will take place in April next year. And Jihan accepted our invitation, which we are very happy about. And we very much look forward to his talk, where he will tell us more about his work. And that will be next year. So please watch out for the announcement. And now I would also like, to give the word to Jihan. Thank you.
Okay, thank you. So I'm very honored to receive this award. I'd like to thank the editor Anne and the members of the editorial and the advisory board of this journal for the recognition of our work. And I also want to thank my students who work on this project, and as well as my institute and other funding agencies for supporting our research. And I hope this event a great success. Thank you.
Thank you very much, Jihan, and also, congratulations to you again, and also to your students, and for this great work that you submitted to us. And we really look forward to your award lecture in April. And the date will be announced next year. And I think with this, I would now like to hand over also to Charlotte, who will proceed with the scientific or introducing the scientific part of this symposium. Thank you very much.
Thank you, Anne, and congratulations, Jinghan. Now let's move on to our first speaker for today, who's Tati Fernández-Ibáñez. I will give a short introduction, won't take long, so stay tuned. Tati received a PhD in 2006 from the Universidad Autónoma de Madrid under the supervision of José García Ruano and Carmen Maestro. She was a postdoctoral researcher for 3 years in the group of Ben Feringa before she moved back to Madrid to work first at the Medicinal Chemistry Institute at CSIC, and later at her alma mater, where she was appointed assistant professor in 2012. She moved to the University of Amsterdam in 2017, where she was appointed associate professor in 2017. Tati's research focuses on developing new catalytic systems for asymmetric transformations and CH functionalization reactions. And today she will talk about ligand-promoted CH functionalization reactions. Tati, we look forward to your lecture. Please share your screen now.
Thank you. I will now start sharing.
Yeah, perfect.
No, wait a second, because I did something wrong. No, I don't see it in a proper way. No. No. Yeah, now you can see it?
Yes, I can see the slides. I can see your pointer.
Good. Then, first of all, thank you for your kind introduction and for the invitation to EurJOC, and also to do these virtual symposiums that I think nowadays is really important to keep the community together. And it is a pleasure to share with you the chemistry that we do in my group that is related with the CH functionalization. And we believe that CH functionalization is an ideal approach to introduce complexity in organic molecules. For example, the synthesis of this biaryl, which is an intermediate for these value-added chemicals, is nowadays made via Suzuki coupling. For this Suzuki coupling to occur, you need to pre-functionalize the starting materials with a halogen and a boronic acid. And these pre-functionalizations, they need to be installed. That means you are adding extra synthetic steps to the whole sequence. Moreover, these pre-functionalizations are not part of your target molecule, and therefore they came out as a waste. If you look at the bottom part of your slide, you could really realize that it will be ideal if you could make this carbon-carbon bond by doing the coupling of carbon-hydrogen bonds. In that way, if you use, for example, oxygen as an oxidant, you will have as a waste only water. Then using CH functionalization, you will reduce the number of steps and then also the time. You will reduce the waste formation and you also reduce the cost of the process, which I think all these issues are really important for the sustainable synthesis of chemicals. And yes, it is possible that we now know in organic synthesis to functionalize inert CH bonds. And there are many ways to do it, but the most common way nowadays is still using transition metals that they insert into the carbon-hydrogen bond to form a metal complex that can be further functionalized. Nevertheless, as I say at the beginning, this is in principle an ideal approach, but still there are some limitations that need to be overcome before this strategy can become a routine synthetic tool for organic chemists. These are the low reactivity of the CH bond, and because of that, we need to still do high temperatures, long reaction times, high catalyst loading, but even like that, the yields are still moderate, and the substrate scope is still also quite narrow. Another problem that we face is the selectivity. How we are going to control the selectivity in molecules that contain diverse CH bonds. For that, you can use, for example, the intrinsic reactivity of a specific carbon-hydrogen bond, but obviously that approach can only be used in certain type of molecules. Or you can use, for example, which is the most common approach nowadays, is to use directing groups. Directing groups, they are just functional groups that can coordinate with the transition metal and then deliver the catalyst proximal to a carbon-hydrogen bond. Nevertheless, I mean, this approach is extremely useful, but in many cases, these directing groups are not part of your molecule, and therefore they need to be introduced and removed from the substrate, which is adding 2 extra synthetic steps to the whole sequence. And a really attractive alternative to the use of directing groups is to use ligands. Nevertheless, in the field of palladium-catalyzed CH functionalization reactions, there are not many ligands that have been proved to be useful for these transformations. I want to highlight 2 of them. That is the pyridine-based ligands, which have been used in the CH functionalization, for example, of not directed adenes, and monoprotected amino acid ligands that developed by Jin-Kwan Yu. Nevertheless, these ligands, they have been always used in many cases in combination with a directing group, where the directing group is controlling the selectivity of the process and the amino acid is increasing the reactivity. In our group, we also want to use the approach of using ligand to promote and CH functionalization reactions. And we have the idea that maybe having bidentate ligands where one of the functionalities is a carboxylic acid unit could have a beneficial effect in CH functionalization reactions, since it is well known that carboxylates can interact with the hydrogen that is going to be transferred in a concerted metallation deprotonation mechanism, and then promoting this CH bond cleavage, which is in general the rate limiting step. With this idea in mind, we came out with these SO ligands, which are extremely easy to synthesize, just one-step synthesis from commercially available alpha-bromocarboxylic acids. I also want to mention that these ligands, as far as I know, they have never been used in metal catalysis, and only 2 studies about their hemilabile properties in palladium chemistry were reported. And we evaluate these SO ligands in the CH olefination of simple arenes, particular benzene. We use an excess of the arene and 5 mol% of the catalyst. And we already observed that when we stop the reaction after 2 hours, in the reaction without ligand, we only obtain 16% yield. Nevertheless, by using our SO ligand, we could reach yields around 70%. We tested many SO ligands with different properties. And for this transformation, we observed that the SO ligands, that they have an alkyl group at the alpha position and a phenyl group attached to the sulfur atom, they are the ones that they perform better. Just to say that this is not about yield, this is a real acceleration. Here you can see the kinetic profile of the reaction without ligand and in the presence of the SO ligand. And the first time, it was already 2017 that I saw these results. I was extremely happy. But taking into account that we use a strong oxidant, then I thought that maybe it was not the thioether, it was the sulfoxide, the one responsible for the catalytic activity. We then synthesized the sulfoxide and the sulfone, and we observed that indeed the yields are similar to the reaction without ligand, indicating that probably this sulfoxide or sulfone are not responsible for the catalytic activity that we observe. We also kind of proved that the bidentate coordination is important, since when we use a thioether or a methyl ester, the yields are not so high that when we have these SO ligand, free SO ligands. And we also proved that the sulfur atom seems to be key in this ligand design. We then did the substrate scope. Don't worry, I'm not going to bother you with all these results. I want to highlight 3 important points here. In all the substrates that we tested, independently of the nature of the substrate, it means with electron-donated substituents or electron-withdrawing substituents, also more or less bulky arene, we always observe that the yield using our ligand is always much higher than without ligand. In some cases, it's quite remarkable. We also observe that the reaction takes place mainly at the most electron-rich position of the arene. And that although we still get mixture of regioisomers, we clearly observe that the ligand has an influence on the regioselectivity of this transformation. And I highlight these 3 examples, which is quite clear to see this effect. For example, with the naphthalene, we go for a 1-to-1 mixture to a 2-to-1 mixers in the presence of our ligand, or in the case of the anisole or phenol, without ligand, the para product is the main product, and in the presence of our ligand, the ortho product is the main product that is formed. Just mention that we did the screening with different olefins, and the reaction seems quite general, using activated olefins, and in some cases also with unactivated olefins. And this is just a general thing. I will not discuss further this olefin scope, and this is just general. And we want to, we were like aiming to go 1 step further. And when I told you, when we did the substrate scope, we were always using an excess of the arene because that it was cheap. It was benzene or anisole, and we could use 10 equivalents. But our goal was to apply this methodology to complex molecules. And for that, you cannot use 10 equivalents of the arene. Then we were really happy to see that indeed we were the first ones capable to do the CH olefination reaction using the arene as a limiting reagent with 1 equivalent in the CH olefination of this, for example, a strong derivative or naproxen derivative. And here you can really see the results, how the reaction is really accelerated by the presence of the SO ligand. In both cases, we obtain almost a 3-to-1 mixture of regioisomers. Then, taking into account that that the reaction was taking place mainly at the most electron-rich position of the arene, we thought that maybe using our catalytic system, we could synthesize 2 free disubstituted thiophene which are difficult moieties to synthesize via other routes. For example, if you do CH functionalization in a free substituted thiophene, what you will get is almost a one-to-one mixture of regioisomers of the C2 and C5 olefinated products. Just want to mention that it was one exception to this trend using this ligand that it was described in 2017. Then with this idea in mind, we decided to test our catalytic system using 5 mol% of catalyst in the CH olefination of free substituted thiophenes. And we were really happy to see that this work was published in EurJOC last year. And indeed, the reaction was taking place as we expected at the most electron-rich position of the arene, and we could increase the selectivity. For example, the reaction without ligand, it provides, when we have a metal substituent at the free position, almost 2.51 mixture of products. And by using our SO ligand, we could increase the site selectivity to almost 9 to 1. And we observe also the same trend with different alkyl substituents. And also it was really visual to see that with the phenyl, when we have an aromatic ring, because it is obviously bigger, then the selectivity without ligand is almost 1 to 1, and in the presence of the ligand is 3 to 1. Nevertheless, when we increase the electron density of this aromatic ring, that means making this C2 position more electron rich, then we could also increase the site selectivity to almost 5 to 1. Then we also moved forward, and then we were really curious to see what it was the effect of our catalytic system in for the olefination of anilines, because anilines, first of all, are widely present in many natural products or products with biological activities. But what it was really important to realize with anilines, first of all, in the field of CH activation, the common approach was to have here a directing group and then do the ortho-CH olefination. But in the case of remote CH functionalization, and in particular para-CH functionalizations, what we observe is that anilines, they are not good substrates for CH functionalization reactions, because in general, the substrate scope is quite narrow. For example, in all these cases, the reaction proceeds via almost electrophilic metallation, and only unsubstituted anilines or anilines bearing electron-donated substituents are being olefinated or functionalized via CH functionalization reactions. And this is because if you put an electron withdrawing substituent in the aniline, then this aniline is not so electron-rich anymore, and then the reaction does not take place. And if it takes place, you need higher temperatures, but these type of anilines are just not stable. It's why these CH functionalization reactions are not really suitable sometimes for anilines. I just want to mention that there were 2 exceptions to this trend. One for the CH arylation and the fluoromethylation of anilines, where electron withdrawing substituents were admitted in the aniline substrate. Then with this idea, we start to check our catalytic systems with the simple anilines, and we did not observe the formation of the desired product. Nevertheless, we were extremely happy to see that by using one equivalent of the aniline and performing the reaction in dichloroethane at 40 degrees, we could obtain the para-olefinated product in very high yield and excellent site selectivity. Just want to mention also that we were able to do the same reaction using oxygen as the oxidant, but just because it's more practical, we continue our screening using this other oxidant. Then we did the substrate scope. We first studied unsubstituted anilines to see the effect of the substituent that is attached to the nitrogen atom. And we observed that in the presence of our ligand, 10 mol%, one equivalent of the aniline at 40 or 50 or 60 degrees, we obtained really high yield for the para-olefinated product, excellent site selectivity, slightly lower in the case of morpholine. And here in this case, it's also slightly lower, but we could obtain the para-olefinated product in synthetically useful yield. And just, we don't know why the reaction in this case without ligand, it does not take place. We also did the olefination of ulidenine with a very good yield. We then decided to test what is the effect of different substituents in this aniline substrate. And we were really glad to see that indeed the reaction works pretty well when we have electron-donated substituents, very good selectivity, slightly lower in the case of methoxy, which is normal because this is also directing and the selectivity to this position, but it's still really high yield, and the para-olefinated product could be isolated in a synthetically useful yield. In the case of phenoxy, very good yield, we only see the para product. In the case of phenyl, we observe that the reaction is slightly sensitive to the steric hindrance, and is why the yield is a little bit lower, but we did not optimize this entry. Then I think we can get it a little bit higher. And again, really happy to see that the reaction is also compatible with electron withdrawing substituent, with 1, with 2, also with ester. The exception is the nitro group. In this case, the yield is still, I mean, this is 2 electron withdrawing, and then the yield is still really low. Then, in accordance with the high selectivity that we observe, the para selectivity that we observe, when we have a para substituent, the reaction does not take place, which is kind of expected. But what it was unexpected in that moment is that when we have an ortho substituent, also the reaction did not take place. And the answer for that is what is going on is that to avoid the clash between this alkyl group or any substituent at the ortho position with the methyl group of the aniline, what is happening is that the nitrogen goes out of the plane, and then there is no delocalization of the pair of electrons of the aniline with the aromatic ring, and therefore this aniline is not electron rich anymore, and then the reaction does not take place. Then we easily solve this issue just by using, instead of a tertiary aniline, a secondary aniline, in this case using a benzyl protecting group. And we were really happy to see that indeed we could do also the para-olefination of orthosubstituted anilines. Here is the substrate scope, again, extremely general. In this case, we only observe the para-olefinated product, and sometimes we observe this formation of this side product that is coming from the CH olefination at the phenyl ring of the benzyl protecting group. And we mainly observe it in the reaction without ligand. And again, the reaction really general with electron donating, also with electron withdrawing substituent. The nitro group, again, is the exception. You could see that here the acceleration or the increase in yield is not so remarkable, but we can have 2 or even 3 electron withdrawing substituents in your aromatic ring, and the reaction proceeds with a moderate to high yield. And we were also able to do the same type of CH olefination using primary anilines. In this case, we need to have the 2 positions and the 2 ortho positions substituted. And what we observe here is if we have an ester group, the ortho position, the reaction is really general. You can almost have whatever other substitution in the aromatic ring, that the reaction proceeds quite well. 1 electron withdrawing, 2 electron withdrawing substituents. And we think that is something to do with some kind of hydrogen bonding between this ester and this aniline. But if you don't have an ester, we observe that the reaction is really sensitive to the electron density of the aromatic ring. For example, if we have 2 electron withdrawing substituents, then this aniline is 2 electron poor, and then it does not react efficiently. But also, if you have 2 electron donating substituents, also the reaction doesn't work well. And we think that what is happening is that your nitrogen becomes too electron rich, and then it coordinates too strongly to palladium, and then it just kills the catalyst. And you could really observe this effect of the electronic density of the aromatic ring in these 4 examples, that you really need to keep a balance, for example, between electron donating and electron withdrawing substituents in order to have a synthetically useful yields. We further applied these methodologies to the CH olefination of indolylines, which are important structures in many, many natural products. And in this case, I just want to highlight that the reaction is not so general that in the case of anilines, because, for example, if you have electron-donated substituents in the aromatic ring, this indolenine becomes too unstable, and then you cannot perform this CH activation, although it's at 60 degrees. But for the rest, the reaction tolerates electron withdrawing substituents attached to the aromatic ring, also substituents at the C2 or C3 position, and also much more complex indolenines. They were in all cases olefinated in good yields, from good to excellent yields, I would say, and excellent selectivities. And we further apply this methodology also to tetrahydroquinolines. In this case, the reaction was much more general, and we can also do the CH olefination having electron-donated substituents attached to the aromatic ring. And again, really general, dependently of the substituents that you have at the C2 or C3 position of the tetrahydroquinoline. Then, taking into account that we were able to olefinate tetrahydroquinolines, that I just mentioned here, in a really selective way, we thought that maybe we could apply our methodology or our catalytic system for the divergent total synthesis of this family of natural products, that they all differ from each other only in the structure of this olefin. Yes, we first decide to test if our catalytic system will be able to do this CH olefination in a selective manner, an efficient manner. We use this as a mother substrate, and as expected, since this is an amide, when we did the CH olefination, we observed quite a moderate to low yield, only 23%. Nevertheless, when we have an oxygenated functionality at the C5 position, which is present always in all this family of natural products, we were really happy to see that we could do the CH olefination in a synthetically useful yield. And we now have applied this methodology to the divergent total synthesis of 10 different diaquinolone natural products. And then with this talk, I hope I have convinced you that we have a really powerful catalytic system for the CH functionalization of aromatic compounds. And I want to end just thank you the people that did their work in the lab, especially Kanana Natsonbon, a former PhD student, now she's back in Thailand, and Wenlian Ya. Also, NWO and the other financial support from DSM and the Cost Action House. And thank you for your kind attention.
Yeah, thank you very much. Very nice. I really enjoyed this. Oh, my camera is not working, huh? Yep.
It's working. No, now no.
Oh, let me see. What is... Oh, it has a problem. Anyhow, let's start the discussion. I try to fix this when the internet gets better here. I have my first question would be directed to the ligand design, because you stick very much with the same ligand. And so I was wondering, when I look at the ligand there, why is this, you could vary this a lot. So is this the result of a long optimization and you stick to the perfect ligand now, or is this still ongoing? So I would be interested to hear a bit more about this.
Yeah, really nice question. Indeed, I mean, at the really beginning for the CH olefination of simple arenes, we did a huge screen, especially because we were aiming to control more the site selectivity of the process. And we test many ligands. And after that, we kind of stick now to this ligand. Nevertheless, now we find out that there are other ligands with similar structure. I mean, SO ligands that they now are giving better results in other type of transformations. Yeah. Mm-hmm. And now we are again coming back to this screening of ligands.
Great. Okay. Let me see. From the chat, something is coming in there, right? Okay. When are you using the sulfur-based ligands? What about the dimerization of sulfur? Because you work under oxidative conditions, and I think it's a sulfur ether you always have. But did you observe you mentioned the concern of the sulf oxidation, so the oxidation, but do you also see kind of other transformations on there ongoing?
No, what we observe, for example, is that when we have, when we use, for example, like chloroethane as a solvent, sometimes we observe the formation of the ethyl ester.
Okay.
But regarding the oxidation, because it is a question that everybody, I get often.
Right.
We don't observe the oxidation of thioethane to sulfoxide, but even we can take the ligand and put metachloropropylene acid or oxidants that we use, and we don't observe that oxidation. I think it's something to do with just the carboxylic acid. You know, it might be something that is avoiding that oxidation. And we don't observe it. We just also take the ligand separately and the complex, because we have some complexes. And the oxidation is just not taking place.
Right. Okay. Here comes another question. Does methionine works as a ligand?
Again, sorry?
Methionine, so the amino acid methionine, does this work as a ligand? Because it looks a little similar.
No, it doesn't. We tested.
You tested. All right, good. I would have a question to the chirality, because you have a chiral center in your ligand. So what is the active, if the active palladium catalyst then has two ligands, you may have kind of different stereoisomers on the ligand, on the metal complex. What is known about the active palladium species for your processes?
Okay, in general, when we do this, we try to isolate complexes and then characterize. We always use the hendimethyl to avoid the formation of diastereoisomers. And right. And what we observe is that if we use, let me see, because I need to recap now. I think what we observe is in some cases when we have a complex with one ligand, and I think when we have an isopropyl instead of the hendimethyl, we observe diastereoisomers in the context that our sulfur atom become chiral.
Right.
And we observe mixture of diastereoisomers, and we also try, in collaboration with Professor Kokotos, to do this the synthesis of these ligands in a chiral fashion, and we are still thinking on working on that.
Right. Okay. Used as oxidants, your tertiary butoxide, so the peroxide on there, and oxygen. Do others also work? Because you mentioned that the peroxides are of course convenient on small scale. Oxygen would be probably good for large scale, but is this restricted to these two conditions, or are there others?
It depends. It depends a lot of the catalytic system. Like, for example, with the thiophene, that it was just published in EurJOC, we can also do it with BQ, with benzoquinone, for example. We can, in general, it is not really restricted with the oxidant. We can use quite a lot of oxidants. It's just that the yields, sometimes are not so high, but it's quite a general thing. I would say,
Right. Okay. And there's another question here from the audience. Is there any interaction between the oxidant and the ligand? Would that help to improve the yield? Or in more general, you also did not kind of refer so much to the mechanism of the whole reaction. So what is the oxidant oxidizing? Is it oxidizing the CH bond by CH abstraction? Is it oxidizing the palladium intermediate on there? Maybe you can briefly refer on this a little bit.
Yeah, we believe it is. I mean, we did quite a lot of mechanistic studies, and we have a very good picture, I think, of what is going on. And just the oxidant is just oxidizing the palladium. We also did we observe zero order, for example, in the oxidant, just meaning that it is not really involved in the rate limiting step. And then,
Okay, good. Okay, so this would be then going on. Last question. Do you have tested ortho-directing groups in combination with your ligands? You showed us in the talk how you were able to overcome in the anilines the ortho substituent, but did you use also ortho-directing groups in combination?
We use once, benzoic acid once, that means your carboxylic acid, the ligand, the directing group, but what we observed is that it was not acting as directing group.
All right.
That means the reaction was not taking place mainly in ortho, it was taking place in other positions.
Yeah. And maybe one very last question for me. You showed us how you nicely can functionalize the tetrahydroquinolines. Can you also functionalize tetrahydroisoquinolines? Because they have these very highly activated benzylic amine functionalized position, which is typically oxidized under oxidative conditions on there. Did you try the tetrahydroisoquinolines?
No, we didn't try. We didn't try because I am a skeptic. I think, maybe it could work, but it will take some effort. It can work because at the end, I think there are possibilities, but we didn't try, being honest.
Right. Okay. So in the interest of time, we have to move on. The attendees can still place questions in the chat, and Tati will answer in writing on there. But with this, I hand back to Charlotte, and I try to work on my camera. Sorry, Tati, but
it's okay.
The program doesn't let me.
I'm getting used to talk to just, I know. Thanks.
Yeah, I think we've all gotten used to technical issues with such virtual platforms. But I hope for our next lecture, everything will work out fine. Our second lecture for today will be given by Joseph Moran. Yes, there he is. Camera works. All right, so before we start, a short introduction. Joseph received his PhD in 2009 from the University of Ottawa under the supervision of André Beauchémont. And afterwards, he worked with John Pisacki and Michael Crichet before he moved to the University of Strasbourg for a habilitation with Jean-Pierre Sauvage. He's been appointed professor at the University of Strasbourg in September 2018, and he's currently the director of the Complex Systems Chemistry International Graduate School. Joseph has received numerous awards for his work in the field of systems and supramolecular chemistry applied to catalysis and to the chemical origin of life. And the most recent that I would like to mention is the ERC Consolidator Grant. His lecture today is titled Metabolism Before Enzymes. Joseph, the stage is yours. Please share your screen. And you are still muted.
Okay, great. Of course, that's the classic problem. Okay, you see my screen fine?
Yes, I can see your screen and I can hear you.
Great, fantastic. Okay, well, big thanks, Charlotte and Burkhard and Anne and the whole team at the European Journal of Organic Chemistry for organizing this wonderful symposium series, and thanks to Tati for the great talk. Like everything she said, I say the same thing. It's great for the community to have these online lectures, and I'm so glad to get included in this and to tell you about the experiments that we've been doing that suggest that the first step in the origin of life was the onset of a reaction network similar to biological metabolism. Before I go there, though, I'm just going to tell you a little bit about our lab's research. So we work on organic chemistry and catalysis at the interface with other fields, such as biochemistry in the case of today's talk, but also at its interface with optics and physics with Professor Ebbeson's group. And to remain grounded in our core expertise, which is organic chemistry, we also work on the development of new synthetic methodology. So, okay, before I get started here, I just want to acknowledge up front that in 25 minutes, there's no way I can do justice to all of the previous thinking and experiments that have shaped my vision of the origin of life. I have to give credit to the people shown here and to many others who come from really all different fields. So geology, chemistry, biochemistry, evolutionary biology. If you want to dig deeper, our group wrote a recent review on this topic listed below with nearly 300 references. Okay, here we go. Once upon a time, 4.5 billion years ago, our planet had just formed. It was a hot and hellish place, and it was bombarded by objects big and small, and there was no life. But if you fast forward 300 or 700 million years later, depending on who you ask, we start to see evidence for life. And this might sound like a long time to us organic chemists, but geologically speaking, it's as soon as low temperatures in organic chemistry become possible. Now, we'd probably all agree that both heredity and metabolism are essential to life, but which of these came first in the origin of life? And this is actually a major point of debate in the origin of life field. But to properly address this, I think we'll need to question some of our assumptions about what life really is. Okay, so if I asked you the question, what is the fundamental unit of life? Probably most of you would answer the cell, or maybe you'd say an organism. So I personally think that's the wrong answer, though why one would say that is completely understandable. So cells are individuals, so are we. They have some sort of visible distinction from one another. And from there, it would follow that each cell or organism has its own genes. So it's easy to conclude that the first step in the origin of life is the origin of genes and genetic molecules. And the thinking is that once genetic molecules existed and could copy themselves, everything else, including metabolism, would emerge later as a result of Darwinian evolution. This is the kind of line of research that most organic chemists follow on this topic, and it's known as the genetics first view of life's origins. Okay, but we come to a very different conclusion on life when we look at things from the perspective of life's chemistry. So metabolism is the word that we use to describe the set of all life's chemical processes. It's everything that builds it up, it's everything that breaks it down, including genetic molecules, and it's the thermodynamic reason that life exists. But a complete metabolism doesn't exist at the level of a cell or even an organism. It exists at the level of an ecosystem. And that's why effectively all organisms eat others or are eaten. But it's harder to visualize because an ecosystem is a bit further removed from our everyday experience. But when we regard the ecosystem as the fundamental unit of life's chemistry, then cellularity and Darwinian evolution can be viewed just as mechanisms that allow that chemistry to be partitioned and locally optimized. And this naturally leads to a view of the origin of life in which metabolism plays the first most basic role. So it's driven into existence as a means to dissipate energy in the environment. And from this, genetics and compartmentalization emerge as useful byproducts, leading to organisms later. So this view is popular amongst many biochemists and evolutionary biologists, but far fewer chemical experiments have been done from this angle, and that's the gap my lab has tried to fill. So what should we expect the first stages of the origin of life to look like in general terms? So here I think we can learn a lot from the fields of non-equilibrium systems and from complexity science, and I want to make 3 points. Okay, so first point, energy and the kinetic channels through which that energy flow are of the utmost importance. So throughout science, we see dynamic structures displaying spontaneous order, like a hurricane. They emerge spontaneously when exposed to just the right source of energy and just the right conditions, because those conditions constrain the release of energy in a very specific way. And we call these self-organized structures dissipative structures. We should expect the same from the emergence of life. We should look for a sort of chemical hurricane. And this means identifying conditions and catalysts that constrain the release of that energy in such a way that it leads to self-organized chemistry. Okay, second point. Metabolism looks like a self-organized system. So one of the hallmarks of a complex self-organized system is that it is built from the superimposition of a small number of simple mechanisms, which, when combined, results in complex behavior. And a classic example is this computer game called Conway's Game of Life, shown here in the bottom left of the screen. So in this game, simple rules act on black and white pixels, and they lead to these complex lifelike patterns that you see here. And metabolism also shares this trait. So most of core metabolism uses just 6 reaction mechanisms over and over again. And that's probably because it began as a self-organized chemistry in an environment that allowed those 6 mechanisms to operate simultaneously. Okay, third point. We should expect that prebiotic chemistry was not drastically different from the chemistry we see in metabolism today. Now, this is a controversial point amongst chemists in the origin of life field, but why do I say it? Well, self-organized systems produce organizational hierarchies in which higher levels of organization result naturally from the activities at lower levels. Now, as a result, fundamental changes at lower levels of complexity cannot occur without disrupting the higher levels. So try changing or adding rules to the Conway's game of life game, for instance, and you'll get totally different patterns or no patterns at all. So in the context of the origin of life problem, this means that whatever chemistry gave rise to Darwinian evolution and all the machinery that requires, ribosomes, DNA, proteins, etc., it would be nearly impossible to drastically change the underlying chemistry that supports all of those functions without collapsing the entire system. So evolution is powerful, but it's not magic. It still has to work within the confines of chemistry, physics, and the principles of complex systems. And that's why I and others think that prebiotic chemistry should roughly resemble metabolism today. It should still use the same key building blocks and the same types of transformations. And this is a satisfying prediction for us organic chemists, actually, because it means that our theory on the origin of life should explain why life's chemistry works the way that it does up front. And that brings me to what my lab is doing to understand the origin of life. So if life really did begin as a self-organized reaction network and was not drastically different from today's metabolism, we should be able to reproduce much of its chemistry without enzymes, and then infer from those conditions the energy sources and the environment that produced it. So based on the latest thinking from evolutionary biology, we've taken a minimal set of metabolic pathways that would get us from CO2 to genetic molecules, namely RNA. And the flow of matter starts here with CO2 fixation, pathways that do that, the acetyl-CoA pathway and the Rtca cycle or reverse Krebs cycle. Then we'll need gluconeogenesis to make our sugars. We'll need amino acid biosynthesis to make our amino acids, about 4 or 5 of them, probably enough. And finally, we'll need ribonucleotide biosynthesis, which comes from amino acids and from sugars. Now, for each of these pathways, we search for simple catalysts and conditions that cause them to occur without enzymes. And if we are successful in doing that for many of these pathways, we should be able to triangulate from those conditions to identify life's primordial environment. That's the idea, anyway. Okay, so we first began our work with life's CO2 fixing pathways. And surprisingly, despite 4 billion years of evolution, there's only 6 different pathways that life uses to fix CO2 to make the molecules that support metabolism. Of these 6, there are 2 that are thought to be the most ancient, and there's only 1 that doesn't build onto already existing biomolecules. And that's the acetyl-CoA pathway, also known as the Wood-Langdal pathway. Now, this pathway is found in both the bacteria and the archaea, which are the 2 major branches of the tree of life. And evolutionary biologists think that this pathway was already present in life at the time of its last universal common ancestor, or LUCA. So on a chemical level, what this pathway is doing is it's reducing one molecule of CO2 to carbon monoxide, and it's reducing another molecule of CO2 transiently to a formal group and then down to a methyl group, which is bound to transition metal cofactors. Then there's a migratory insertion to give a new CC bond forming acetyl-CoA, and then a reductive carboxylation to give pyruvate. So this is biology, but I'm using the language of transition metal catalysis here because essentially every step in the mechanism of this pathway involves transition metals, either in the cofactor or in the enzyme itself. So could this pathway have operated with metals alone before enzymes altogether without all the big organic fragments? And we think the short answer is yes. So after failing at much more sophisticated ideas, we eventually noticed that any of the native or zero-valent forms of the metals used by the cofactors and enzymes of the acetyl-CoA pathway react with CO2 in warm water to produce formate, methanol, and acetate on the near millimolar scale. And in the case of metallic iron, nickel, and cobalt specifically, pyruvate is also produced. This is like a really ridiculously simple experiment, but I think it's possibly the most important one of my career. Basically, the same metals used by the biological acetyl-CoA pathway without any enzymes fix CO2. They produce the same C2 and C3 intermediates of the biological pathway and essentially nothing else. So to explore this further, we focused in on metallic iron because it makes up 80% of the core of the Earth, and it's the most important metal for biochemistry, at least in my opinion. And we found that the reaction works over a broad range of temperature and pressure. In fact, at 30 degrees Celsius and 1 bar of CO2, the only products are acetate and pyruvate that we could detect, at least. And this is, to my mind, nearly ideal prebiotic chemistry because it's just iron and CO2 and water. It does chemistry that mimics a metabolic pathway, and it's extremely robust. Okay, so I should say, though, the organisms that run the acetyl-CoA pathway don't use metallic iron as the source of electrons to fix CO2. They use hydrogen gas. It's a hydrogenation. Okay, so these tend to be organisms that live in hydrothermal vents, the bottom of the ocean, where hydrogen gas is abundant. So we teamed up with Bill Martin, who's an evolutionary biologist in Dusseldorf, who'd long promoted the idea of a non-enzymatic acetyl-CoA pathway, and with Harun Tusuz, who is a specialist in heterogeneous catalysis at the Max Planck Institute in Mülheim. And we found that, that several iron-based minerals, in fact, that are present in hydrothermal vents, such as magnetite, which is basically rust, greigite, which is an iron-sulfur mineral, and awaruite, which is an iron-nickel alloy. They're all able to promote the hydrogenation of CO2 to get the same products I mentioned before, including acetate and pyruvate. So these minerals are catalysts. They don't change during the reaction as determined by Harun's team by XRD analysis, and so we consider this to be an even closer non-enzymatic mimic of the acetyl-CoA pathway. Okay, so the second CO2 fixation pathway that I'd like to tell you about is the Rtca cycle, also known as the reverse Krebs cycle. So this one's important because it contains all 5 of what I call the universal synthetic precursors to biochemistry. So what do I mean by that? Well, all fats are ultimately made, or all lipids are ultimately made from acetyl-CoA. All sugars are ultimately made from pyruvate. All amino acids are ultimately made from pyruvate, oxaloacetate, or ketoglutarate, and some cofactors are made from succinate. With those 5 molecules, we can build up all of biochemistry. They're all present on the same cycle, and it's the only cycle that has that feature. Another unique aspect of this cycle is that it's autocatalytic. So we start off with acetyl-CoA, which is 2 carbons. We build up to oxaloacetate, which is 4 carbons, continue building until we get to citrate, which is 6 carbons. But then this splits into 2 and gives us back 1 molecule of acetyl-CoA and 1 molecule of oxaloacetate through a retro-Aldol reaction. But what this means is that each turn of the cycle doubles the number of molecules. And this has a potential then for exponential growth, which is really interesting for prebiotic chemistry because it could help concentrate material into the critical building blocks for life. So we weren't the first to try to recreate the Rtca cycle without enzymes. There had been some early attempts by George Cody at the Carnegie Institute, and probably the most successful attempts came from Scott Martin's group at Harvard University. So they showed that the semiconducting minerals like zinc sulfide and manganese sulfides could act as photocatalysts for 2 of the reduction reactions of the Rtca cycle by using UV light and electrons from H2S. But that's it, though. They weren't able to string together successive reactions. So our approach to this was to divide the Rtca cycle into 2 sequences. And to make our lives easier to begin, we chose only the ATP-independent steps of the Rtca cycle. So the first sequence involved the reduction of oxaloacetate to malate, its reversible dehydration to fumarate, and its reduction to succinate. The second sequence involved the reduction of oxalosuccinate to isocitrate, its reversible dehydration to aconitate, and its reversible hydration, but now on the other carbon to give us citrate. Okay, so to search for conditions where these reactions would occur spontaneously without enzymes, we screened for temperature, pH, a variety of different reducing agents, and as catalysts, we looked at a variety of metal ions. And here's what we found. So many different reducing agents were able to accomplish the reduction reactions, but our friend metallic iron did it best. Zinc 2 was the best of the metal ions for promoting the 2 first dehydrations, with iron 2 being the second best. 5 of these 6 reactions could be carried out at 70 degrees Celsius in mildly acidic water. The lower 3 reactions in the sequence even worked at room temperature if we used micelles. So for instance, oxaloacetate went on to malate, onto fumarate, onto succinate, all of its own accord at room temperature in water if we use those micelles. Okay, so the same thing was true more or less for the top sequence. Okay, so at 70 degrees Celsius, we could reduce oxaloacetate to isocitrate and eliminate it to aconitate. However, the only really tricky reaction of these 6 was the very last one, the hydration of aconitate to citrate. Okay, so other conditions that we screened, only chromium-3 was able to promote the reaction, and only under quite forcing conditions, 140 degrees Celsius in 1 molar HCl. Under those conditions, all 6 of the reactions work. That's probably too harsh to be relevant to the origin of life, but considering how easy the other 5 reactions are, it seems plausible that a better heterogeneous catalyst could one day be found that could allow this last reaction to happen under mild conditions. We only looked at simple metal ions. So in any case, the important point is that all 6 of the ATP-independent reactions that we tested work non-enzymatically, and they can even work under just one set of conditions without enzymes, just using simple metals and metal ions. So what about the ATP-dependent reactions of the Rtca cycle? So they're very important to our hypothesis, of course, because those are the ones that form CC bonds. Though it's a bit too early to talk about it today, we now have some promising results using inorganic analogs of ATP to make these reactions work. But 3 years ago, that wasn't the case. And at that time, we decided to consider alternatives for how these CC bonds could be forged in ways similar to biochemistry, but without a phosphorylating agent. The only problem was we didn't have any idea what biochemistry would actually look like without ATP because, life is based on ATP. But lucky for us, a group of biologists in Boston were wondering exactly the same thing, but from a totally different perspective. So Daniel Segre's team was considering the idea, which had originally come from Hyman Hartman, whether metabolism may not have originally started off with all of the elements that we know today, C, H, N, O, P, and S, but whether some of those may have joined later. And if that was the case, metabolism would exhibit a layered structure like you'd find in an onion. So what they did is they took all metabolic reactions in the KEGG database, they turned it into a network, and then they saw what happened when they removed certain elements. When I say removed, it means that the element doesn't appear in the starting material or the product or in the chemically critical part of the cofactor, if one is necessary. So when they removed sulfur, they got a really sparse network, but when they removed phosphorus, this is the network that they got. Each dot represents a metabolite. Each line connects those 2 dots, represents a biological chemical reaction that interconverts them. And the bigger the dot, the more connected it is within this network. So with phosphorus gone, a huge part of core metabolism was still intact. And all 5 of the universal precursors to metabolism that I mentioned before, they're all present. Those are the compounds that I've circled in black here. Of those compounds that are made up only of C, H, and O, the 2 best connected ones were pyruvate, which I just told you we made from CO2 and iron, and this one, glyoxylate, which is a reactive aldehyde, circled in red. Okay, so this map suggests that if there was a metabolism that could function without ATP, it would have relied very heavily on those 2 compounds. And while I now think that actually some of those assumptions that are made in this model can't be justified, I do in fact think that activated phosphates are very important to the origin of life, but there was already evidence from Springsteen and Krishnamurthy that the Aldol reaction between pyruvate and glyoxylate could happen without enzymes and without even any catalyst to form a new CC bond. So we wondered, what would mineral catalysts do to such a system? So when pyruvate and glyoxylate are mixed in the presence of ferrous iron at 70 degrees Celsius, a network of reactions occurs, which generates many metabolites. It also produces CO2 and very little else. So this plot shows 16 of the compounds that were produced and how they change over time. The network involves 9 of the 11 intermediates of the TCA cycle, and all 5 of those universal precursors to biochemistry that I mentioned earlier. And we also found that if hydroxylamine, which actually is an intermediate of nitrate reduction, and metallic iron are both added, then 4 biological amino acids are also produced. So, all these metabolites, it's hard to figure out the mechanism. So what we tried to do is to piece it together. We subjected all of these intermediates back to the reaction conditions. We followed them over time in the presence and absence of pyruvate and glyoxylate. And we also did experiments with C13 labeled glyoxylate and with 3 different C13 labeled pyruvate isotopologues. And then we integrated all that information together and we proposed the following mechanism. So the first one is the Aldol reaction, again, between pyruvate and glyoxylate, no surprise there. That gives us hydroxyketoglutarate, which dehydrates to give oxopentene dioate. It's reduced to ketoglutarate, which is part of the Krebs cycle. That undergoes another Aldol reaction with glyoxylate to give oxalohydroxyglutarate. It undergoes an oxidative decarboxylation to isocitrate, and then there's a very slow retro-Aldol reaction that occurs there that gives back glyoxylate and produces succinate. But in fact, most of the succinate seems to be coming from another reaction, which is the oxidative decarboxylation of ketoglutarate. Succinate interconverts with fumarate and malate, but also these two keto acids also decarboxylate oxidatively to give fumarate and malate. Malate is slowly oxidized under the reaction conditions, which gives oxaloacetate. It rapidly decarboxylates, giving back pyruvate. When iron is added along with hydroxylamine, all of the amino acids are converted. All of the keto acids are converted to the corresponding amino acid by formation of the oxime, followed by reduction. So pyruvate is reduced to alanine, glyoxylate to glycine and reductive amination, ketoglutarate to glutamic acid, and oxaloacetate to aspartic acid. I should say that nature doesn't use hydroxylamine to make amino acids, but this roughly parallels the biosynthetic transformation. But what I think is really cool about this network is that the types of reactions that make it up are the same types found in central metabolism. So I think it might have some relevance to their origins. In fact, if we take those reactions in that network and we map them onto known biological cycles, they overlap substantially. So 9 of the 11 intermediates and 7 of the 11 reactions of the TCA cycle, also known as the Krebs cycle, are represented. That's just the reverse of the Rtca cycle that I told you about before. You're running it right now as you sit on your chair, digesting your lunch and breaking down your molecules to CO2. 8 of the 9 intermediates and 5 of the 8 reactions of the glyoxylate cycle are also represented there. So maybe these pathways too have their roots in non-enzymatic chemistry. But in support of this, so just this year, there was a paper from Krishnamurthy and Springsteen. They showed that the non-oxidative reactions that I showed you on the last slide, they also occur even without iron in the presence of phosphate buffer, which acts as an acid-base catalyst. And the oxidative reactions that I showed you that were happening with iron in our case happen with H2O2 in their case if they add it in separately in a separate step. So their experiment requires more intervention from the experimenter than our setup, but it shows that there might be more than one way to make this sort of chemistry happen without enzymes. Okay, so that's all I have time to show you today. So I showed you that we've seen non-enzymatic versions of the acetyl-CoA pathway of CO2 fixation. We've seen rough analogs of the Rtca or TCA cycles. We've seen non-enzymatic amino acid synthesis from keto acids. In a longer talk, I would have also mentioned Marcus Rahlser's work on a non-enzymatic analog of glycolysis in the pentose phosphate pathway. That's the pathway by which sugars are broken down in biology. But I also would have told you about our unpublished work on a non-enzymatic version of gluconeogenesis, the pathway by which life builds up its sugars. And we've also identified a more biology-like non-enzymatic way to make amino acids that are a little bit more like biology, that don't use hydroxylamine, and which makes it more compatible with other types of chemistries and metabolism. And finally, we're exploring a non-enzymatic version of the biosynthesis of pyrimidine ribonucleotides, starting from sugars and amino acids, more like how they're made in biochemistry. So yeah, as Charlotte mentioned before, fortunately, I was very pleased to find out just last week that this work will be supported by the ERC for the next 5 years. So look out for more non-enzymatic metabolic pathways coming soon. And so even though this project is still in the early stages, I hope this talk was, for organic chemists, made you consider the idea of a non-enzymatic origin of metabolism, maybe for the first time. And I hope you got to think differently about the origin of life, or maybe for the first time, and maybe even differently about life in general. So I've already shown their names and photos on the appropriate slides, but I am truly grateful to the members of our group, both past and present, and our collaborators who've helped make this project a reality. Thanks also to the ERC and the Marie Curie Actions, Volkswagen for paying the bills. Thanks again to the European Journal of Organic Chemistry, Chemistry Europe, for inviting me to be part of this fantastic symposium series. And just a quick plug for Strasbourg. Strasbourg is one of the capitals of Europe. Good food, great sites. When the pandemic is over, please come visit us. I'll be happy to take questions. Thanks.
Yes, thank you very much for this very inspiring and very lively talk. Fantastic chemistry, really showing new kind of perspectives on the origin of life on there. I particularly liked your chemical hurricane. Very nice. That's a very cool term. I like this. Excellent. Very good. Let me start with a few questions. We've seen that reduction is necessary.
Yeah.
CO2, and to make pyruvate, you need 8 electrons. And you gave us different sources of electrons.
Yeah.
So hydrogen and H2S, iron, elemental iron. So can you put this in a perspective? What is kind of the most, because this is very different chemistry, how you reduce things by these different sources. Do they work together, or is one of them maybe the preferred one?
Well, so I guess the people who are biology oriented would answer that hydrogen gas is the preferred one, because it's the one that's used by the life that does these sorts of pathways today, usually. But it always proceeds through the intermediacy of a ferredoxin, which is a reduced iron cluster. So I don't know if you can really make, I think you could also argue for reduced iron being a potential source of electrons from a biological perspective. From the chemical experiments that we've done, metallic iron is reducing CO2, and it's also reducing it's doing all of the reduction reactions in the Krebs cycle, in the reverse Krebs cycle at the same time. And we've also been able to do reductive amination with it. So I would say just from the experiments that we've done, metallic iron seems like it's the best. But in fact, it may well be that in the experiments that we've done with hydrogen gas, that metallic iron is actually transiently generated in the reaction. There's also another example which I cited but didn't talk about with electrochemistry that's also produces acetate and pyruvate. It uses an iron sulfur mineral as the electrode, and minus 1.1 volts, which at that such reducing potentials, that probably also reduces a little bit of the mineral to metallic iron. So I don't have an absolute answer to that, but metallic iron keeps popping up over and over again, and yeah.
Right. Yeah, you really showed that iron seems to be special and very important. And here are questions coming in from the attendees. What about the other metals such ruthenium, nickel, chromium, rhodium? Are these considered prebiotic minerals? So are they present to a large extent? Because you mentioned iron is currently and was at former times the major mineral.
Right. Yeah, so I wouldn't rule anything out at this stage, because it's always possible that you have one reaction catalyzed by a relatively rare metal, and then it gets taken over by, once you have better organic molecules that act as ligands. I actually used to make that argument in the past that, like in the same way that human society developed catalysis and ligands, maybe prebiotic chemistry might have done that. So to take an example, one of the first homogeneous hydrogenations was done with ruthenium and were done with ruthenium and rhodium, right, in acidic water, without any ligands. And then over time, chemists figured out that you needed to make these complex ligands, and then you can use iron to do homogeneous hydrogenations, right? It may have been the same thing in life, so that's occurred to me, but yet it's not really what we seem to have needed so far. So I haven't had to go that way yet, but it's always been in the back of my mind. So it's a really great question.
Okay. You mentioned in one part of yourself that you also used micellar conditions.
Yeah.
And so here the audience seems to have read your articles quite in detail. ACS reviews on there. So micellar conditions, but at the same time, could this be relevant for prebiotic chemistry? So what was first? Was first the fatty acid, the micelle, or was first the chemistry there to make it?
Yeah, so I would say, it's kind of so I bring that up. That particular example was done with a micelle that is not prebiotic at all. Okay, so it was done. So we did it without micelles, of course, and the reaction works. It just requires 70 degrees Celsius. Whereas if you do it at room temperature with micelles, it works better. But the specific micelle that works was the Lipschitz micelle, okay, which is obviously not prebiotic. And what's unique about that micelle compared to, we tried about 30 of them. What's unique with that one is that it forms nanoscale environments, whereas other ones are much larger. So I think there's something unique maybe about the nanoscale that's not specific to that micelle, but could be reproduced in other ways. So maybe the pores of minerals, for instance. So we're looking into that actually.
Yeah. So this points to the importance of probably interfaces,
Yes,
or segregation,
absolutely,
or microstructuring. So,
yeah.
so you share this view that this is of importance for this kind, for the chemistry to develop.
Yes, absolutely. Absolutely. And so we're currently, actually just today, we received 40 grams of some minerals from a collaborator who's a geologist. And so we're going to screen those. So far, we've been mostly screening things that you can buy from Sigma Aldrich, but we're moving more towards geology now.
Right. Okay. Interesting question here. What is the application of research in the area of non-enzymatic metabolic pathways in cancer research? So from your things, can we learn something also for, is there some translational findings in this direction?
Yeah, so I don't work in that area, but I know that, people who do, so Marcus Ralzer is more of a biochemist, and he was the one that I mentioned his name because he had published a paper on a non-enzymatic glycolysis and pentose phosphate pathway, which incidentally also runs at 70 degrees Celsius in the presence of ferrous iron. But he thinks that a lot of metabolic reactions fly under the radar because they're not actually catalyzed by enzymes. And so if we could track that in a bit more detail, we could learn a lot. One application that's not cancer, but it's along, other than origin of life, it's one application of this research. I recently was contacted by some researchers who study soils and decomposition of organics in soils. And they have estimated that 50% of the CO2 generated from organic matter decomposition in soils is non-enzymatic. Or at least not from living organisms. And so we just recently started to write stuff together to study this, to understand what its mechanisms are, if there's any relationship to some of the work we've been doing on the origins of life. Right.
Yeah. If everything started non-enzymatic and so chemistry was running, for me the question would be, how did enzymes then take over? They were simply just better and faster. So how you imagine these kind of transition?
Yeah, so that's basically it. So if the network is sophisticated enough to produce organocatalysts, they feed back as better catalysts. Eventually, so the idea is this: you also have to have a path then to making peptides. So that the network has to be able to make peptides. It probably has to make polyribonucleotides as well. But then the peptides can feed back as organocatalysts as well. And so you might have some combination of organocatalysts from what we call cofactors now, and small peptides either on their own or ligated to metals as catalysts. And then once you have translation, then you have kind of a Darwinian evolution regime, which takes over. So the chemistry doesn't change, but the catalysts get better and better. When I say doesn't change, it's not, there might be still changes, but it's not drastically changing.
Right, just improving, right. There's one specific question in one of the cycles you showed that the transition from the acetonitrate to citrate, this is a difficult one, where this one would only work with chromium-3. Yeah. Why is this such a difficult reaction?
Actually, don't think the reaction is difficult. It's because I think what we did is that we only looked at homogeneous catalysts. And so what we believe is the catalytic species is an oxyanion or like when you aquate chromium-3 at really acidic conditions, 1 molar HCl, it forms oxygen-bridged dimeric and higher order species. And we think those are the catalysts. And the same is probably true for zinc, actually. Incidentally, there's enzymes that actually use these oxygen-bridged zinc in the synthesis of pyrimidine ribonucleotides. So what we're trying to do now is to look at both minerals and also clay-supported zinc and chromium species to see if they can catalyze under much milder conditions, because we think that it's really the cluster formation that's the hard part, not the actual reaction.
All right. Okay. Right. And then there's one question I have to ask as somebody working in photochemistry.
Sure.
Well, so Joseph, do you believe that life could have evolved without light?
No. I mean, I would say absolutely no.
Okay, good to hear.
I didn't invoke any light in my talk today, right? So I still, I get asked this all the time because I work with biologists who are big supporters of hydrothermal vents. Yet a lot of my organic chemistry colleagues who take a very different approach to prebiotic chemistry are very focused on photochemistry. I haven't really picked a side. I mean, I would say that, but I would still say yes, because even if it's not directly relevant to the first prebiotic chemistry, which it still might be, I haven't made up my mind, but it is still absolutely essential to even the earliest evolution of life, because even if life was happening in a hydrothermal vent, what drives those is the redox gradient at the planetary scale. So the core of the Earth is 80% metallic iron, 20% roughly metallic nickel. And as you get to the less dense phases, you get to the atmosphere, that's, you have some water vapor, which is split by sunlight into UV radiation into H2 and O2. The H2 escapes into space because it's got a low escape velocity, and O2 is left behind. It reacts with the reduced material on the surface. But what that really creates is the entire planet becomes a battery, and that battery is responsible for everything from tectonic plate motion to everything that goes on the geological scale. So hydrothermal events really wouldn't exist if it wasn't for that redox gradient. So one way or the other, light is essential. Whether it's directly required for the first chemistry or not, I haven't made up my mind. Many people have strong opinions, but
right. Yeah. Thanks a lot. So that was really inspiring, very nice area to look at. And we saw this already from the response from all the attendees, right? Good. So I think now on the program, and Charlotte should help me with this. So we are now assembling for a little chat. Is this right?
Yes, absolutely. Joseph, I think you can stop sharing your screen now, because, yeah, perfect.
And we would like to
All right.
Tati, back on screen. You're still there?
Yes.
There
Yeah,
she is.
very good. Right, good. Because what we thought in these days, when we all do these virtual symposia and lectures, we all know this. You are invited somewhere, you give your talk is over, last question is asked, and then you're in the front of a black screen because the host has pushed the stop broadcasting button on there. And we thought we should kind of be a little different here and do something, what we call in German, the Nachsitzung. Typically we go for a dinner, then to talk about the science a bit more, but also talk about things next to the science on there. And this is what we wanted to do here today. And there are a few topics I think that as scientists are of interest for us, because these are special times. So my first question to you would be, how do you kind of run your day-by-day science in your groups under these conditions where there is social distancing? At least for myself, I find this difficult that I'm not meeting the co-workers in groups, and we gather together or have a coffee and whatever. So how do you handle this, that you are still can give constant feedback and are in discussions with your co-workers? Any of you can start.
You want to start, Tati, or should I?
I don't know. I think Tati is just
so maybe I'll start while she recovers. Yeah, it's a great question. I don't have a perfect solution for it because it's just not the same. But well, we've kept the same structure of our meetings, so we still have like one weekly full group meeting, and then subgroup meetings that alternate every week depending on subgroup. So that hasn't changed. Our full group meetings are now over Zoom. They're not done in person. Our subgroup meetings are still in person, but we're spread out in a big room that's like for 60 people. So if we have 8 people, it's fine. And so we're all wearing masks and that sort of thing. So those meetings have not. So the structure has not changed. Our lab is still running. So I can still like walk into the lab. It was much harder in the first lockdown in France because then the lab was completely shut down.
Oh,
and
right.
we did a lot of literature meetings. So we were going. Every person was presenting a paper from a different journal every week, and we did a lot of literature. It was good for that. I did a lot of writing, a lot more than I normally do, like on stuff I would never write normally or have time to write. We wrote a 37-page review, but yeah, it definitely killed the interactions. I mean, we'd have occasional subgroup meetings. We also have a Slack group Slack. both by topic, so we could chat by topic or chat through the whole group or chat one-on-one, but it's not the same as being in person.
Right. Yeah. I think everybody has to find kind of new. Interesting that you mentioned the reviews. I think this was also something recognized by the publishers. No, and after the first lockdown, there was these kind of boost of review articles set in. Hi, Tati. So you're back.
Yes, I have some connection suddenly, you know.
Yeah, we are just talking about how we handle under the current situation the contact with the groups or the discussions with co-workers. How do you do this in Amsterdam?
I mean, what I try to do is to go once a week to the lab, and then I have a real discussion there. And during the lockdown, I was just at the really beginning having a hard time because I have 2 small kids. And then it is really difficult to have Zoom meetings with 2 kids around, you know, then I was really struggling. Yeah. But I think now, because now we are facing a second lockdown in the Netherlands, I think things will be better and easier. You know, like, you know already what is happening, then maybe to pick up at right times, you know, that kids are maybe doing other things, whatever. But yeah, I mean, if you can't, if you have the possibility to go to the lab, it's always the best, because at the end, I always have the feeling that it's not exactly the same via Zoom, you know, like sometimes you want to see the spectra, you know, and it's just not the same. But I think it's a solution for what we are living now.
I think this is something we all experience, no? I think it shows us the situation, how important the direct interaction and also the kind of informal discussions about many things are for life and human interactions, right? Another important thing, of course, is to bring people into your group. And this is, of course, always critical, no? How to hire people, how to build your group, no? And you, as let's say as the more younger researchers, this is even more critical, no? So you have financial resources, you have brought in, or you have made some great achievements on there, and then you have to bring in people. And we all know good people in the group spirit, and bringing people in, that's important, no? And how do you kind of select this? And now here, Joseph, you now got all the, you're now a rich man, you got the big money, so you have to hire someone. And I would be, this is something that's always also interesting for people outside. How do you do this? You get the applications, when you get an application to your group, for a postdoc, let's say, and you open this, what are the factors you look for? What makes you reading the whole email or reading the CV, and what makes you sending back a no thank you email? No?
You want to start, Tati, or?
Yeah. Whoever.
Okay. Well, so that has changed a lot over time. So when I started, you know, when I had 4 people in the group, I didn't get many applications, or I got applications from all over the world. But I think there's certainly if you know somebody that somebody that knows this person, or you know them personally, or you've met them at a conference, that will always be a factor that I think will give you some confidence, because when you're starting out, you know, if you make one big hiring mistake, it can have a huge impact on your lab. So I tried to rely more on either people. I didn't hire anyone I knew, but I hired people that I knew at least from 1 degree over, or as much as I could. But then that slowly changed, and then I would always make sure to. I realized later from mistakes I made early on that you know, the social nature of the person is also really important. So now I always, you know, before I hire them, bring them for an interview and have them meet as many of the people in the group as possible, if they haven't been, you know, if we haven't met them already. So there's exceptions to that where I knew the student when they were doing their PhD or something like that, and so that wasn't necessary.
But how do you do this now? Because you cannot invite people in from there's no way to travel.
That's true.
So now you have to hire by a video call, or how do you do this then?
Yeah, well, the last 2 people that we hired, again, we knew them. You know, one of them I knew personally. One of my coworkers knew personally. So I didn't have that issue. But from email applications, let's say, I'll look at what group they come from, what they published, how well the application is written and formatted, and whether there's some personalization in it. Because if it says dear esteemed professor, I know that's I'm probably not going to want it's not directed towards me. It's like a spam email. So it definitely showing that it's personalized, then have some knowledge about your group, about the types of research that you do, or they might describe some talk they saw you in or some paper of yours they read. That would also make a huge impact.
Do you answer all emails? Email application?
No. What do you?
Okay. Too many.
No, it's not that I get that many. But I answer the ones that are personalized.
All right, good. Yeah, I would say. Tati, how do you do this? How do you bring great people to your group?
It's a little bit the same that what Joseph, because Joseph mentioned almost everything.
Sorry, you go next first.
Yeah, like for example, with PhD students, in general, is for recommendation letters, someone that I know that say, okay, this person is good. Then I do the interview, and sometimes even if in the interview they don't perform excellent, I really trust these recommendation letters, and so far I'm really happy with that. And then if I don't know the person, is the first thing I will look is in the cover letter. If it's something general, like dear, even if they say Fernández-Ibáñez, it doesn't matter, just the name, but it's just they talk about themselves, then I see they don't have really interest of what I'm doing. It is just one extra application, Then I think it is important to personalize, like, I want to do the postdoc PhD in your group because, that they talk a little bit of what you are doing. That I think is important when you don't have a contact person.
Right. Yeah. No, I think the personal aspect is very important, so that it's what was mentioned here, no? So it must be not a kind of general application on there. I would fully agree on this. It is probably the same way I also would do this. Right. So, but it has become more difficult, I think, in this current situation, because normally you meet people on conferences on there. And at least within Europe, whenever possible, I try also to invite people in, that they come in, that they join the group on there. And how important is the group response to a candidate? So you like the candidate, has good recommendation, but the group says no. What do? Group is never
extreme.
Okay.
The group is always right.
The group is always right. Oh, that's very wise. Okay.
I will first ask why not. What are the weak points that they saw someone that is really controversial? I don't know. I think first I would like to know why they think that person is not suitable in the group.
Right. Okay.
And depending on the answer, then I will be more or less convinced.
Right. It's an extreme case, right? Another topic I would like to ask your opinion on is, because this is something I experienced over the last, 10, 12, 15 years. In older times, when a project was done and we write the paper, the content was very important, but now also the order of the author names has become super important. And I remember times where in chemistry, this was not important. So sometimes the senior author or the correspondent was last, and some people even put them first. No? So there are some older colleagues who are always the first author and the corresponding author. Others did this alphabetically. So they ordered all the names alphabetically. No? And we were always kind of wondering why this is so different in the bioscience, because there was always a lot of discussion on this. But now in chemistry, this has become a very, very big thing. How do you handle this? Do you fix the list of authors already before you start your project, or when does this come up? Or is this a problem at all, or is it always falling into easy things? Tati, say something.
So far, I didn't have any problem with that, but I know what you mean, because in my PhD, my supervisor, he was corresponding and first author, and the rest we were with alphabetical order, which I really didn't like, because then when you write your CV, you need to explain, like, really, I did that work, in the lab. Yeah. Anyway, for now, I mean, in general, because I always allow the students to write their own papers, and then they make more or less their own choice of who are the order of the authors. And so far, I did not get any complaint, and I think everything. And I did agree with the order of the authors. Then so far, so good.
Yeah, they should know. No? If they have done the work, they should know who did what.
I think so, yeah.
Yeah. Joseph, you are so close to the bioscience, and the origin of life is a very, very hot topic, competitive also, international. How is this in your lifetime?
In terms of author order?
Yeah. Is this always easy, or is this a point of debate?
I think most of the time it's been pretty easy. I haven't, I'd say the vast majority of the time, my feeling on like I will often ask privately the suggestions of each author on the paper and ask them what they think, and then I compare it to what I was thinking, and it's almost always the same. I've only encountered one time since I've been a group leader that we've had a dispute on a paper. I've had other times when one of the authors comes to me and says, I'd actually like this other author to be co-first author with me, because we really, we're equal and you put me first. But it's actually very nice things that they've done. But I've had one dispute on an authorship where, one person was original. So that was when I was first starting the group, and I kind of wrote an early draft of the paper before it was completed, and I wrote an author list, and then the person who was first author kind of just dropped off and left the work to the later authors, and so then by the end of it, I felt that the order needed to be inverted, and that caused a big disagreement. So that I learned from that, and now I don't write the author list until right at the end.
Right. Yeah. It's you can only say this when the work has been done and when things have been finished.
Exactly.
Right. No, that is it's interesting that this has become important, but I think many of the journals also react on this, no? So that the contribution list, I think, is also changing how you are name the contribution of different authors, how you make this in a way to make this better visible in a way. And also, of course, we have these days much more collaborations also with other groups, and then these things have to be taken into account, right? These are also days where you can't go to conferences and you cannot invite guest speakers to the institutes and have a chat about science. And so where are your new ideas coming from? Is this you can read, of course, that's possible, but at least for me personally, for the creative process to find new things is for me always involved with other people. So discussing, talking, reflecting things, and this is not so much possible right now. And how do you feel this situation when you are fixed to your computer and reading things on there? So where do inspiration comes from for the next big grant or the next great project?
I agree with, the inspiration is now coming from reading, but it's just not the same because you don't get the same input. Also even inspiration or even the projects that you are doing in conference, sometimes you have really nice questions that you say, oh, that's true, I should try that, to improve this or that. And now this is missing. This is I'm just waiting forward that this will change and we can have the opportunity soon to meet in conference.
That's right.
Yeah. In our case, so the origin of life, one of our groups is subgroups is origin of life, and that project, the literature is so broad and so diverse that there's so much to read that I haven't read. Whereas in organic synthesis, I read. You look at the big journals and the various journals in organic chemistry every day, and so after a certain amount of time, we're all reading the same literature, and there's to some extent. But origin of life is just, it dates back sometimes 70, 80, 90 years. Even before origin of life was a field, there's biologists and biochemists doing research that you should know about. There's geologists. There's so much back reading I had to do that I never got bored with. And my other project with we do on with optics, with Professor Ebbison. So having the collaboration always bring fresh things, because he's always doing something that I don't know or understand, and I need to learn it, and vice versa, I imagine. And so, it didn't suffer too much from that yet, but if it went on any longer, I think, if it goes on for another year, then I think we'll then start to suffer.
I can understand this because your field indeed has a lot of interfaces, interfaces to other subjects, and what many people say, that new things develop at these interfaces because you get an inspiration from something you don't know so much about, and you look at it at a different perspective. And I can imagine if you have many of these interfaces, you still get a lot of creative input.
Yeah.
Well, when you are working in a field which is kind of classic catalysis or synthesis and so on, there it's maybe even more important to have these kind of discussions on it.
Absolutely, I think so.
Good, yeah. Maybe one more point to publishing, because now we cannot travel, so we have, I don't know, at least I thought I have more time, but this is not really the case. But we can write things and publish things on there. When we publish, of course, review reports come back on there. And how do you handle this then? So you share this with your group. So then first response comes from the involved students in your group to this one, and then you discuss this, or how do you handle this if the paper is not accepted right away, but there are some minor revisions to do? So how do you handle this then?
Yeah, Joseph. Well,
the first thing I usually do is if there's the rejections that you're like, okay, I understand, and there's ones that you're like, but I might just share it with the co-authors, and then we discuss and we decide collectively on a plan of attack. If it's stuff that I think they can just respond to, I usually give it to them to draft the first draft of the response letter. We have kind of a template for doing that, and so they just do the first draft, and then we sit together and edit it together later before sending. And if it's a total rejection where we have to just, where there's not much feedback and we can't really change anything, we just have to change to a different journal, then we just decide what journal send it to, decide if there's anything major we want to change about it, and then resubmit. I mean, yeah.
Yeah, it's probably the way most people do. I'm just asking because some time ago a colleague told me that when review reports come back, that they were not shared with the co-workers because sometimes these comments are so hard, and because we notice, so sometimes it can be a very hard critic coming back to the work. And so there was the idea of protecting the co-workers, having them in the soft bubble of great research on there. I also don't do this because I think one has to experience the tough life in science early on. No, Tati, how you do this?
Yeah, no, I'm thinking when you need to do minor or major revisions, I always share with the co-authors. If it's like a total rejection, in general, I just discuss more informally with the co-authors why it was rejected. Sometimes I could complain, maybe not, if I agree or not. But I mean, if it's just that we need to do things, then it is just fully shared with all the comments and everything. If it's just fully rejection, then I just say to them, it didn't work. We need to try another journal.
Right. Okay. Yeah.
I don't shuttle them either. I just, but I might preface the sending of the review with a few lines about what I think of the review, just to protect them in that way. But I wouldn't withhold the reviews from them.
Yes. Yeah.
I actually find this really helpful to get also feedback, especially from the PI in these difficult cases. So I remember I had one case where the PI was perfectly right, and they complained about how this was really tough on the students, what had been written in the report.
I always try on the reviewer's end. I try, even when I'm harshly critical of something, I try to phrase it in a way that is minimally, you have to think about not just the PI, but you have to think about the students and postdocs who are reading that review too. So I try to do that.
When I give author workshops and talk about peer review, I always tell people that you have to make sure that the way you phrase your criticism of a paper is not overly critical, because by that you won't really have the person on the other side on your side. They won't even try to understand what you meant to say with your criticism, but they will just be like, yeah, but this is not correct. So if you really want to help someone improve their paper, the tone of your report really matters. Yeah.
I actually have a question a bit related to that. So what's your publication strategy? So how do you decide on where to submit the paper? Do you discuss this with the student, or do you ask the students for recommendation first and then give your opinion on it? Like, how do you make the decision on where to submit the work? Is it together with the students, or do you make the first suggestion?
It depends. Like for me, at least, there are some cases that I have it clear. Like I think this should be this or this kind of paper, you know. And sometimes I just also have doubts, and then I discuss with the author. What do you think, you know? And then sometimes they just want to try a different journal, and then we have a discussion. And sometimes we try the journal that they think is more suitable, and sometimes the other one that I think is more suitable. But yeah, sometimes I have it more clear, and sometimes I give a little bit more room for discussion.
Yeah, I pretty much do the same thing. I mean, I have always my own idea in my head about where I think it's appropriate for. I'll ask the student, but then I very often ask colleagues too who are work on it. I just ask one of my colleague organic chemists who works down the hall or across the street, just ask them what they think. Or sometimes it's not even like, friends who I did my PhD with who are now professors elsewhere. I'll just send them an email like, do you think this is a viable submission for this journal? And then they write me back with like a one-line. That helps. Just getting feedback. That's what and I tell them, don't hurt my feelings. I don't care. I just want to hear what you really think.
I think it's very important to get to do these kind of discussion and reflect the topic, because particularly when you work in a topic and you really like it, and you're really into it, then you start losing kind of, I would not say using the judgment, but if you like something really, in a way, you may value it a little too high. No? That can happen too. No, I think it's a good strategy, right? Good. So I'm looking here to the time. No, so I think we have to slowly come to an end.
Yeah, maybe to close the session, because we actually have a question from the audience. So the question is what we think how the current situation will affect the number of publications in future years. And when things will go back to normal. And I think that's interesting because we actually talked about this before the event started. And Anna and I mentioned that right now we do see an impact of that. Numbers have dropped. But I also feel that it's really difficult to say what the impact will be for next year and for the years after that, because it's still so difficult to say what the situation will actually be like in 3 months, in 6 months, in 9 months, and so on. So, yeah, I wonder what you think about this, and how you also experience it right now in your groups.
Then, in my group, it really has the COVID an impact, especially because in the first lockdown, it was like almost 3 months that the people was not working in the lab. Then you can just not produce results, and the number of publications obviously will be much less. Yeah, and then after the lockdown, little by little, people was working. Still, not everybody could work full time. Then now it looks more or less we still keep the 1.5 meter distance, obviously, and one fume hood empty. Then we still, our capacity is not at 100%.
Yeah.
And there is an impact on that, obviously.
So I don't know about you, that I go through like sometimes waves and troughs of publications where sometimes there's many projects that are finishing at the same time, and then you're just sending out lots of papers, and then sometimes all projects are in kind of that early development phase, and then they don't come out. So for us, this year's been kind of that development phase. I mean, about the end of last year, we started working on a bunch of new projects that are kind of all in development at the same time. So we submitted a lot less papers than we did the year before this year, but it's not really because experimental papers. It's not really because, well, it's because of the lockdown to some extent, but I'd say it's equally because of just where we were in that trend.
Yeah, I also would say that in places where the research can go on, certainly also results are produced, and this is still the case in many places, many labs, that lab work can go on. Of course, if there's a complete lockdown and people send home, there's no lab work, there are no results, no? Because we are in experimental science. This is how it is on there. But I think the long-term impact will be also on the way we kind of communicate, the way we teach, the way we do science. So I'm pretty sure we will travel less to lectures because this will be something I'm pretty sure we have to reconsider. It doesn't make sense to have, let's say, 10-hour travel to give a 1-hour lecture and then, of course, talk to colleagues and so on. I think that these things will be different in the future. So you will go somewhere and you will stay at least a few days and value more the direct interaction, while when it's just a lecture in a seminar, you can do this also by these virtual things on there, just to explain your chemistry and discuss things a little bit on there. I think this will change, and the same thing also for committee meetings and many other things on there, where you travel, meet, and leave on there. I hope that responsible people will think about this. Is it really necessary, or can we do other means to do this? So that will be certainly a change on there. But publication overall, I think this will not so much affect it unless, as I said, if there's a complete lockdown, of course, then there is no results produced in a way. But otherwise, I think. And how long does it last? I don't know. No, I heard today in the news that next summer 60% of the German population should be vaccinated. I don't know if it's indeed very difficult to predict a little. I guess we may have still some restrictions in 2021. At least. Right.
I would love to see these week-long conferences, like Gordon-style conferences that are having, but where there was a bit more kind of forced interaction at dinners, because what I find is that you sit down at dinner and you find somebody that you like, and then you end up talking to them over and over again, which is good. But I wouldn't mind getting in the same way we have these forced breakout rooms to make you meet more people.
Mm-hmm.
See that.
I think there is development in these virtual symposia, and let's see what we all get used to this in the teaching, and we will also probably use it more for other events. No? I recently attended a symposium organized by a Swiss foundation, and they even had a virtual apéro. So an apéro kind of, and they had also breakout rooms, and you can meet them with people and talk about Christmas, about the science, and so you could decide what kind of group you would like to enter on there. And so I think this is an experimenting how things are ongoing. Well, it's fun. Right. So I think with this, I will give then the last word here to Charlotte, I think, or Anna, I don't know, who will close the thing. Thank you, Tati. Thank you, Josef, for being with us here and sharing the chemistry. That was really amazing. And I saw we had here close to 200 people joining. So I think this is a very good way to keep on distributing science, to have people from kind of all over Europe or even further apart joining here and enjoying the chemistry on there. And but anyhow, we all look forward to see each other in person again, and hopefully this will be the case next year or sometime in the future. So with this, thank you again, and Anna, hand over to you.
Yeah, thank you, Burkhard. And thank you, all of you, actually, for this really nice and lively discussion. I really hope that our viewers enjoyed it too, although they couldn't participate in person. Yes, so thank you to the three of you for participating today. Also, a thanks to Jing Han, who has left us earlier because it's already pretty late. in Shanghai. As Anna has mentioned, our next event will be in April 2021. And for updates on this, please follow us on Twitter. We will announce the exact date then. So for all of the attendees that are still with us now, thank you so much for joining us today. We hope you enjoyed it. And we hope to have you back next year for our next virtual symposium.
Thank you for the invitation, and yeah, Happy New Year, Merry Christmas, and Happy New Year to all of you.
Thanks very much.
Yes, a happy holiday season to everyone.
Bye-bye.
Bye.